Okay, in this problem, number 35, we're going to be using our calculus techniques to sketch this graph. So that means sign charts. So let's go ahead and start doing that. So take your first derivative, and you get 3 times 2 is 6, 6x squared minus 6x, once again. And I'm going to pull out a 6x, and then that's going to be x minus 1. So I have two critical values. I get them from each factor. My first critical value is 0, and my second one is 1. So get your sign chart. I have a 0, I have a 1. This will be my first derivative up here. This will be my function direction. And then I'm going to go ahead and do a second derivative down here. So I'm going to use my factored form. Pick a number to the left of 0. So pick -1. If I plug a -1 in here, I get a negative. In here, I get a negative. A negative times a negative is a positive. I'm going to have my slope be positive. Therefore, my function is sloping up during that interval. Pick a number between 0 and 1, so let's say 1/2. That'll be positive here and negative here. Positive times a negative is a negative. My slope is negative, therefore my function is sloping down. And then pick a number to the right of 1. If I pick 2, that's going to be positive. That'll be positive. Positive times positive is positive. I'm back to upward sloping. Okay. Now let's do the second derivative test. We're going to do it right on our critical value. So I need a second derivative. So over here, let me just do that. So f prime prime of x will be what? Looking at the first derivative, it's going to be 12x minus 6. Okay, so if you put a 0 in your second derivative, the result will be a negative. If it's negative, then your function is concave down, which affirms what I found with my first derivative test. We're going to do the exact same thing with 1. Plug a 1 in your second derivative. 12 minus 6 is positive, therefore right at the critical value of 1, my second derivative is positive. Therefore, my function is concave up, which is consistent with what my first derivative test told me. So at this point, I would write a statement, and I'm not going to write it in the interest of space here, about the critical values. So I'm going to say critical value statement. So you would say that at the critical value of 0, my function is at a maximum because my first derivative test indicates a slope change from positive to negative, and my second derivative test indicates the function at that critical value is concave down. Okay, for the critical value of 1, I would say that the first derivative test indicates that at 1, since the slope of the function changes from negative to positive, that suggests I have a minimum. And then my second derivative test, conducted right at a critical value of 1, indicated that my second derivative is positive, which tells me my function must be concave up there, which affirms the fact that I have a minimum. Alright, so now let's use this information to graph my function. So I need to figure out something about the y values if I'm going to really graph it. So let's do that now. So if I have a critical value of 0, plug it in your original function, and I get a y value of 0. So therefore my critical point is 0, 0, and that's going to be my max. Okay, let's do the same thing with the minimum. So take your 1, plug it in your original equation. Notice I'm not using a calculator. 2 minus 3 will give me a -1, and so therefore I have a min at the critical point of 1, -1. Okay, I'm now ready to graph this. So look at your original function. I know that the y-intercept is going to be right here at 0. That also is my max of my function. I know the minimum is going to be right here. So if this is my max and that's my min, when I graph it, I get that. Okay? And that's using the sign chart and the resultant statements that I have in this box, and the fact that I have identified a max and a min to graph this function without ever putting it in my graphing calculator. So let's go on to question 36. Okay, this next problem wants us to use calculus techniques to graph this cubic function. So I notice it's a cubic function. I'm assuming I'm going to have one inflection point and perhaps a max and a min. So let's find out where all those things are happening by first taking the derivative of the original function, and we get 3x squared minus 3. Okay, factor this because I'm getting my critical values by setting the factors equal to 0. So I pull out a 3. Now I see I'm going to have x squared minus 1, so I'm going to go ahead and just factor that right away. So I get a critical value of 1 and negative 1. Because I know I'm going to eventually need to have my second derivative, I'm going to go ahead and do that right now. That will just be 6x. So that tells me that I have a inflection point at x is 0. So right now I know I have critical values at 1 and negative 1, and I have an inflection point at 0. So I know a whole lot just taking the first derivatives and doing a little analysis. So now we're ready for our sign chart. So your critical values are what you put on your sign chart. You put them on as if it's a number line. And here's my first derivative test. Here's my direction of my original function, and here will be my second derivative test. Alright, pick a number to the left of negative 1. So let's pick negative 2. If I put a negative 2 in here, I'll get a negative. I'll get a negative here. That makes my slope positive. If my slope is positive, my function is going in the up direction. Pick a number between negative 1 and 1. 0 is the easiest. I would have positive 1 times a negative 1 gives me a negative. My slope is heading down. Then pick a number to the right of 1. I pick 2. That's going to give me a positive times another positive. My slope is again positive. My function is going up. So it appears to me that I have a maximum at negative 1 and a minimum at 1, and my guess is someplace between negative 1 and 1, which is the 0, I will have an inflection point. Now let's use our second derivative test just to make sure that I've done this correctly. Take your negative 1 and plug it in your second derivative. You get a negative 6. Since you have a negative, it must mean your function is concave down, which affirms a maximum. Do the same thing with the 1. Take the 1, plug it into 6x, you get a positive. That affirms the fact that your function is concave up, which is consistent with it being a minimum, as was discovered by the first derivative test. Okay, you would write a statement here about what you found with the critical values. This is essential if you're going to use these results. So you would write a statement, and your statement would say that at a critical value of negative 1, the slope goes from positive to negative, indicating that a max is occurring. Also, the second derivative at negative 1 is negative, which affirms the fact I have a concave down maximum value at the critical value of negative 1. Then at the critical value of 1, the slope changes from negative to positive, and the second derivative is positive, so therefore I have a minimum at the critical value of 1. Okay? So that's your statement. So I'm not going to write it out here because it's very hard to do that. So let's get our values now. If my function is -1, I know I have a max there. So where does that happen? -1 comma. Plug in your -1 in the original function and you should get a 4. So just check my math, make sure that that's right. Then take your other critical value of +1 and plug that in, and you should get 1 minus 3 plus 2. 1 minus 3 plus 2, which should be 0. So that's where your minimum is. Okay, I know that this function has a y-intercept of +2. So now I'm ready to give myself a little sketch. So here is my y-intercept of -2. Then I have a critical value of -1 and +1. So I need to go up to 4. So here is one value, that's going to be a max. Here is my y-intercept, and here is another value, that's going to be a min. So what does this look like? I'm going to come through here, sit on the axis, and go back up. There is my cubic function using only the calculus techniques of sign chart and evaluation of that. And I have my nice graph. So practice doing this. Don't neglect knowing how to write the critical value statement. Okay? So that's the end of this particular section.